So we were just discussing about how the resting membrane potential is being developed in a resting myocardial cell and how that sets the stage for the next phase, which is the action phase of the cell and action potential development which is taking place in the cell. So just for a recap, we know there are sodium potassium ATPases protein, and these proteins are throwing out sodium and gaining potassium. They are throwing out 3 sodium ions in exchange to 2 potassium ions, and we also have leaky potassium channels at the cell membranes which are also throwing away cations. So the net effect is that the cells are continuously losing cations and moving towards negative voltage state, and that is exactly how the cell is developing the resting membrane potential, which is minus 90 millivolts. Now let us see what happens to the stage, the cell, when this particular cell moves from the resting state to the active state. How action potential is generated in a cell and how is it conducted to the adjacent parts of the cell or even to the adjacent cells. So let's see, here we have a myocardial cell. So as explained before, in the resting membrane potential, we have the sodium potassium ATP is here, which is constantly throwing out sodium and gaining potassium. And we also have the closed sodium channels, and we also have the leaky open potassium channels, right? So they are in fact losing 3 sodium ions, 2 gaining of just 2 potassium ions, and in addition to that we have loss of K+ ions. So altogether this is creating the resting membrane potential, a negative voltage state inside the cell, which is minus 90 millivolt. So from here we look onto a graph which represents voltage against time. So in this graph, the baseline, the time is here on the x-axis and the voltage will be plotted on the y-axis. And here at baseline, this is the resting membrane potential, which is minus 90 millivolt. At this particular stage, this cell is being loaded with some cations. This cell is being stimulated. This cell is activated either through gap junctions or through some other mechanisms. These cells are loaded with some cations. So as these cations enter, what happens to the resting membrane potential? The resting membrane potential starts elevating. It moves towards positivity. Because the cell is gaining cations, the membrane potential will slowly rise from minus 90 to minus 80, and at this point it is minus 70 millivolt. Here this is resting membrane potential, and minus 70 millivolt in a myocardial cell, in a contractile myocardial cell, this is what we call as the threshold potential. The minus 90 millivolt is threshold potential and minus 90 millivolt is resting membrane potential. So as the voltage inside the cell touches this minus 90 millivolt, voltage gated sodium channels will be opened. So here we have sodium channels. So these voltage gated sodium channels will open, and we know the cell is a bag of potassium immersed in a sea of sodium. there is high concentration of sodium outside the cell and high concentration of potassium inside the cell. Because of the higher concentration gradient, as soon as this voltage gated sodium channels open, the sodium will immediately flood into the cell. Sodium will be flooding into the cell, and this sodium channels will not be open for a very long period. It is only open for a very brief period. It will only open for a very brief period, but because we have a very high concentration gradient, as soon as the gates are opened, the cations are flooded into the intracellular compartment. Now what happens to the voltage? As the cations are flooded into the intracellular space, the voltage will be going further high and it reaches somewhere around 0 millivolt. So this is phase 0 of depolarization. The cell was polarized. It was negatively charged in its resting phase. So as the voltage gated sodium channels open, cations are loaded into the cell and the cell is moving on towards positive voltage state, and this is what we call as moving away from the polarized state. We call it depolarization. So this is phase 0 of depolarization, or at phase 0 of action potential. Now what happens? I've told you the sodium channels will be only opening for a very brief period of time. Because it opens only for a very short period of time, it closes immediately. So it closes immediately means now there is no more cations coming into the cell, and at the same time we have potassium channels opening here. Simultaneously, potassium channels will be opened. So as the potassium channels open, we know intracellular compartment is high in concentration of potassium. As the potassium channels open, it will start leaking potassium out into the extracellular compartment. So because the sodium channels are closed and because the potassium channels are leaking, immediately after the phase 0 depolarization, the cell will again start, or it tend to lose cations. So it tend to lose cations. So the voltage graph will come down. It starts to come down. So this is phase 1 of action potential. Here the voltage graph will tend to come down because the influx of the sodium is being blocked by the closure of sodium channels, and the efflux of the potassium ions are being opened, are being functional. Because of the opening of the potassium channels, there is loss of cation happening, so that the voltage will tend to dip, it tend to fall, which is phase 1 of action potential. So as it starts to dip, as it tends to dip, I'm sorry, I can just change the color here, otherwise it will be confusing for you. So this is the potassium channel, yes, and potassium, we are losing potassium here, and now we have simultaneous opening of calcium channels. Calcium concentration is higher in the extracellular compartment comparing to the intracellular compartment. So as soon as the calcium channels open, the calcium ions will start flooding into the intracellular compartment. So here we have loss of potassium ions, cations are being lost, and at the same time we have gaining of calcium ions, cations are being gained also. So gaining of calcium, gaining of cation and losing of cation, both are happening simultaneously. Because of the simultaneous losing and gaining, there is no net change in the voltage. This will result in a plateau phase. So this is the plateau phase of action potential because of no net electrical change. We are losing potassium and we are gaining calcium. So there is no net change in the voltage inside the cell, which will result to phase 2 of depolarization, which is the plateau phase. And once if this plateau phase is completed, soon this calcium channels will be blocked. Soon here the calcium channels will be blocked. There is no more calcium coming into the cell, but at the same time the potassium channels will remain open so that the cell continues to lose potassium, so that the electrical potential inside the cell in phase 3 of action potential starts to dip. It dips to the previous or the baseline level, which is minus 90 millivolts. So this is phase 3, and here at baseline we have phase 4 of action potential. In this phase 4 of action potential, the cell will prepare itself for the next upcoming action potential. So just to recap what is happening here, at the baseline we have the sodium potassium ATPase is functioning and the leaky potassium channels. With this property, the cell is losing cations and it reaches a resting membrane potential of minus 90 millivolts. And when the cell is being excited by the influx of some cations, the resting membrane potential will be rising because it is flooded with cations. The resting membrane potential, which will be rising from minus 90 millivolt to minus 70 millivolt. When the electric potential reaches minus 70 millivolt, the voltage gated sodium channels open and the cell will be flooded with sodium cations. As soon as the cell is flooded with sodium cations, there is phase 0 depolarization of the cell. The action potential moves towards depolarization as soon as the sodium channels are open. And then in the next phase we have closure of sodium channels and simultaneous opening of potassium channels. So there is closure of sodium channels. The cells are not anymore receiving cations. At the same time, through potassium channels it is losing cations, so that the voltage tends to dip. But we have opening of calcium channels immediately after phase 1, so that the exchange of cations are balanced, exchange of the efflux of potassium and the influx of calcium are balanced, so that the cell maintains a plateau phase. And after that the calcium channel closes, but the potassium channel remains open, and because of that the cell loses cations and the electric potential moves further down towards negativity and touches the baseline resting membrane potential, which is minus 90 millivolt. So this is called as repolarization. The electric voltage, the electric potential inside the cell have gone to depolarize, and then by the end of the action potential it has gone back to the negative state, it has gone back to polarization. So we call it repolarization. It is now again in the polarized state. So this is repolarization. So depolarization have happened and a short phase of plateau is there, and then you have repolarization. This is one complete cycle of action potential. Now what we need to learn here is these are the electrical changes that are happening inside the cell. Now we need to relate it with the mechanical changes that are happening inside the cell. We know action potential can result in muscle contraction. We know action potential can result in mechanical action of the cell. So how does that happen? How is the mechanical action related with the electrical action? So the mechanical action is related to the electrical action through a process called as electromechanical coupling. So let us see what is happening in electromechanical coupling. We know that every cell, muscle cell, this is a cardiac muscle cell, has small muscle units, and those muscle units are called as sarcomeres. Small muscle units are called as sarcomeres. So here we have the Z line, the outer boundary of sarcomere. We have Z lines, the outer boundaries of sarcomere. And we have a central M line. Then we have filaments. We have thin filaments. We have thin filaments like that. And we have thick filaments. Thick filaments. We have Z line becoming the boundaries of the sarcomere unit. At mid we have the M line, and we have thin filaments called as actin. So these are actin filaments, and we have thick filaments called as myosin. So we have actin filaments and myosin filaments, and these myosin filaments have heads, myosin heads. So all of them will have heads like that. Now, the surface of the actin filaments have sites for the attachment of the myosin heads. So if I expand this actin filament here, please have a look at here. I'm expanding this actin filament here. So this is one single actin filament. So this actin filament have small spores. For myosin heads. So myosin heads are supposed to hook at these spots in the actin filaments. But we have a separate protein over the actin filament which is called as troponin. So this is troponin protein on the surface of actin filaments, and attached to this troponin protein is the tropomyosin filament. So the tropomyosin filaments are aligned upon the actin filament in such a way that the binding sites for the myosin head are not exposed. The tropomyosin filaments covers the myosin attaching heads, or the sites for the attachment of myosin heads on the actin filament during resting phase. Now what happens is that here in the plateau phase of depolarization, calcium is being loaded into the cell. Now this calcium moves and it reaches a special organelle inside muscle cell. We call them sarcoplasmic reticulum. So these organelles are rich in calcium ions. So these sarcoplasmic reticulums are rich sources of intracellular sources of calcium. The sarcoplasmic reticulum are rich intracellular sources of calcium. So in the phase 2, when the calcium channels are open, in the plateau phase, calcium influx happens, and the influx of this calcium will stimulate the sarcoplasmic reticulum to release the intracellular reserves of calcium. So with the influx of the extracellular calcium, it stimulates the sarcoplasmic reticulum to release the intracellular reserves of calcium, and as the intracellular reserves of calcium are released, they go and bind with the troponin molecules here. They go and bind with the troponin molecules on the actin filament. So they go and bind to the troponin molecule of the actin filament. So as the calcium gets attached on the troponin molecule of the actin filaments, this troponin pulls the tropomyosin filament so that now the myosin head binding sites on the actin filament are exposed. Because of the pulling effect of the troponin, the tropomyosin exposes the myosin head binding sites on the actin filament. So as the binding sites are exposed, now the myosin heads are free to attach to the actin filaments, and it pulls the Z line together. So as it pulls the Z line towards the center, the single unit of the muscle, which is the sarcomere, it contracts. So when this happens in every other single units of muscle, the entire muscle bundle contracts. So this is the mechanism by which the calcium influx in the plateau phase of action potential results in the contraction of cardiac muscle. And this entire phenomena of translating the impulses in the electrical impulses to a mechanical activity is what we call as electromechanical coupling. So here an electrical activity has been converted into a mechanical activity, and this is what we call as electromechanical coupling. Now this completes the purpose of action potential. What was the purpose of action potential? The purpose of action potential was contraction of the myocardial cell. So that completes the purpose of the contraction of myocardial cell. Now repolarization happens after phase 2. Repolarization happens. So what happens in repolarization? In repolarization, we have on the cell, we have something called as sodium calcium exchangers. So this is the repolarization phase, and this repolarization phase we have sodium calcium exchanges over here. So there are so many calcium available inside the cell. So all these calcium which has influxed into the cell during the repolarization phase, it will go out. In phase 4, when the cell is preparing to rest and when the cell is getting ready to the next cycle, the calcium within the cytoplasm will be moving out to the extracellular compartment in exchange to sodium. So few sodium ions will be coming out through this calcium sodium exchanger molecule. Now what happens to this sodium? This sodium in the resting phase of the cell, now the cell has reached the resting phase. In the resting phase of the cell will be later taken out through the same sodium ATPase pump. Sodium potassium ATPase pump. So the calcium which has came in has gone out of the cell, and in exchange we have taken sodium from the extracellular fluid that also has moved out of the cell. Now we also have some calcium being released here from the sarcoplasmic reticulum, which is attached to the troponin in the actin filament. So all those calcium remaining here will be taken back to the, so all those calcium will be taken back into the sarcoplasmic reticulum by some special structures here. Here you have some special structures, and these are called as calcium ATPases. We have sodium potassium ATPases here, and here we have calcium ATPases molecules. So these calcium ATPases molecule in the resting phase after repolarization, all the calcium which has been used for contraction of the muscle, all the extra calcium which has been released into the cytosol from the sarcoplasmic reticulum will be taken back. So the calcium released from the sarcoplasmic reticulum has gone back. The calcium which came from outside the cell, from the extracellular space has gone out, and in exchange you have taken sodium, but that sodium is also being taken out of the cell through the sodium potassium ATPase, and that completes the entire process of action potential. So just to recap this segment, we started with resting membrane potential. We have sodium potassium ATPase here, which is continuously throwing out 3 sodium ions in exchange of 2 potassium ions, and in addition we have leaky potassium channels, which sets up the resting membrane potential to minus 90 millivolt at the resting stage of the cell. And when during the active phase of the cell, when the cell is being stimulated, the resting membrane potential rises from minus 90 millivolt to minus 70 millivolt, and this will result in the opening of the voltage gated sodium channels for a very short period of time. And as these gates are opened, there is a sudden increase in the intracellular voltage. So it will move from negatively charged state towards positivity. It will move away from polarity, and that is why we call it depolarization phase 0. And then immediately you have closing of sodium channels so that there is no more cation gain, and at the same time there is opening of potassium channels, so there is cation loss. No more cation gain, but there is cation loss, which means there is a slight dip in the voltage here, but that is for a very short duration, a very brief duration. Immediately calcium channels will open, so the exchange is balanced. Potassium is going out, calcium is coming in, the exchange is balanced, and for that reason we have a plateau phase here. So we have a plateau phase here, and on completion of the plateau phase, the calcium channels are closed, but the potassium channel remains open. The cell continues to leak cations, and the electric voltage inside the cell will dip down back to the pre-excitation stage and reaches the resting membrane potential when the ion exchanges by the calcium sodium exchangers and the sodium ATPases are completed. And in between, in the plateau phase, we have electromechanical coupling. The calcium which is entering into the cell in phase 2 and causing the plateau phase will stimulate the sarcoplasmic reticulum to release calcium, and the released calcium will attach to the troponin on the actin filament, and it pulls the tropomyosin filament, which exposes the myosin head binding sites, and which will result in contraction or approximation of the Z lines of the sarcomere unit, and that will result in muscle contraction, which is called as electromechanical coupling. So that completes the total of action potential and its relation with the mechanical action of the cell.